Another concept that we need to discuss before moving to more advanced topics is the idea of data structures. So we've talked about the idea of variables as a way of holding individual pieces of information. The question remains, can we hold larger pieces of information using only a single variable name? And the answer is, of course we can. It becomes too problematic to store information in individual variables. For example, suppose that I had a survey with 1,000 individuals responding to, let's say, 5 different questions. You're talking about almost 5,000 different variables that you would need just to store that information if we were to use our approach of storing information in individual variables. So what we need is a mechanism to store that information in a very organized way to be able to retrieve it, but also in a very succinct way so that we can very easily retrieve it without having to declare all of these variables with the individual pieces of information assigned to them. So there's 3 primary ways that we can do this in R. And it's through the use of vectors, data frames, and lists. And believe it or not, there's even more data frames out there, but these are the 3 most fundamental types in R. And anybody learning R should become aware of what these types are and learn how to use them. So the first type is what's referred to as a vector. And we had in some sense already seen a vector, but I'm going to discuss it from the ground up. So a vector is like a mailbox system. It's similar to a vector in linear algebra, where you have a collection of numbers, right? That's in an ordered tuple. Except in R, it can be any mixture of things, so to speak. So vectors are ordered starting with the number 1. And again, we can think of it like a mailbox system where we store all the information into a single variable. And then the way we have to think about it is like creating a mailbox system of a certain size, assigning numbers to pieces of information in an ordered fashion, and then assigning this entire mailbox system to a single variable name. The way we do this in R is by using the C function. So we literally use the letter C, and then we do the same thing like what we do with functions when we call it. However, in R, the input to this function is the information itself that we would like to order, and the way in which it's ordered is how we explicitly have written it. So suppose that I have 5 people with different ages, and I want to store their age information. Okay, so age information for 5 people. So suppose that somebody's 30 years old, 25 years old, 41 years old, 24 years old, and 17 years old. So I can store all of this information by creating a vector, by passing that data directly into the C function, ordered the way in which I would like it to be ordered. If you call that function, you'll notice up here in the console that R is going to return back an ordered collection of data, the same data that we put in our input. However, we can't work with this directly because we haven't assigned it to a variable. So this function only creates the mailbox. We now need to assign the mailbox to an actual variable. So let's just say X, or more appropriately, ages. Okay, so now if we take a look to see what's in ages, we can do that by just saying, hey, R, what's in ages? And lo and behold, it will do that. So with vectors, you can do a lot of different things. The most fundamental operation with vectors is seeing what is in a specific position. Remember, R indexes these starting at 1. So it indexes mailbox number 1 here, mailbox number 2 here, and so on and so forth. So this is a mailbox system with size 5. So we say that that vector has a length of 5. Again, very similar to what we had experienced in linear algebra. So if you take a look at ages and you want to pull information out from one of the specific mailboxes, you do this by listing the name of the mailbox system that you've assigned it to, an open bracket, a closed bracket, and then the specific number that you want to refer to. So I want to know what's in the 4th position in this vector. It's 24, and that should make sense, right? Because you did, wait a minute. Because you did 1, 2, 3, 4. Lo and behold, 4 is in 24. Okay, so 4th position of the vector. What if we wanted to change what's in that 4th position? We can very easily do that by just saying, hey, go grab what's in 4 and replace it with some other number, let's say 21. And if you take a peek at what's in ages now, you'll see that in the 4th position, 24 has been turned into 21. We're not limited to only working with one index, though. We can actually pass within the brackets, interestingly enough, one of two things. Either another vector that we define where the vector itself is index numbers, or a variable that contains a different vector of index numbers. So let's look at it from this way. Grab elements at the index numbers 1 and 3, let's say. And we can do that by putting in the braces the definition of a new vector where we put the position numbers of 1 and 3. Doing so, as you can see, R will return back 1 and 3 in its own vector. And then you can store that in a variable and work with that if you want. The second way is to create a variable with a vector of index numbers. So suppose that I wanted to grab all of the odd index numbers, where I create a sequence. The sequence function will return a vector, by the way, from 1 to 5, because I have 5 elements, going by every other number. Okay, so if you do that, and you take a peek and see what's in index numbers, you'll see it's the numbers 1, 3, and 5. And then you can do ages of index numbers, and it should return the odd indexes. So as you can see, 1, 3, and 5. Okay, so working with vectors is a very powerful tool. You can do very similar arithmetic that you can do in linear algebra, by the way. So if you had the incomes of individuals, let's say $30,000, $50,000, I'm sorry, 45,000, let's go with $55,000, $30,000, 60, 50, $65,000, $31,000, and let's say $21,000, right? So you have incomes of individuals. If you take a peek, so we've declared a different vector. As you can see, same deal. Sorry, my phone is going off. Declare a different vector. And now you can do math on the vectors. So if you notice, if you add together the ages and the incomes, right, you'll notice that, oops, sorry, what it will do, and just to illustrate this, let's pull up ages and let's pull up incomes. You'll see that it took the first element and the first element, added them together and stored the result in the first element. Same with the second element, the third element, the fourth element, and the fifth element. So as you can see, it's doing similar arithmetic. The only exception is when you do multiplication. If you remember from linear algebra, the way you multiply two vectors is either by an inner or outer product. This actually does neither. This just simply takes the multiplication of each individual one and gives you a new vector. If you were to add those together, then you would get the dot product, okay, between the two vectors. The inner product, if you remember that definition from the calculus course there. You can do other arithmetic. You can do division. You can look at how much income per age has each individual, earned on average for every year they've aged. Okay, so there's a lot here that you can do with the vectors. The very important part here about the vector arithmetic is that one of two conditions needs to be true about the two vectors that you're working on arithmetic on. The first is that they're the same size, or the second is that one is a multiple of the same size. You can't have a vector of size 4 and size 5 and add them together. That's not going to work. You can add a vector of 5 and 5 as we've illustrated, but you can also add vectors of 5 and 10 because one is a multiple of the other in terms of size. Now you can use vectors as input into functions, and there's different functions we can use that specifically take vectors as input. For example, we have the mean function, which will find the average value of the values, assuming that they're actual number values in the vector. So you can use the mean function to find the mean, the standard deviation, let's say, the total sum, and there's others that you can do. There's range. I think there's range. I forget. Pretty sure. Yep, the range. So there's functions that you can use. Oops. That will take vectors as input, and it will do something to it depending on what those functions are. I'll leave it up to you to use the question mark on each of these functions to see specifically the documentation for them, to see how they're being used. So now the second type of data structure that we work with is what is called a data frame. And a data frame is an extension of a vector. By the way, one more thing about vectors. We can append vectors. Okay, and it's very easy to do this. Basically, suppose we have a new age come in. And we say, I want to append to the vector ages, the age 54. We can do this by using the C function again and passing in just the vector. And what R will do is basically take all the numbers in this vector and put them into the first input. So it's as though you have 5 individual inputs. So if you were to do this, you'll notice that you get 54 appended onto the end of the vector. You can change the vector structure itself by reassigning it to the same name. And if you check to see what's in ages, you'll see that it's now there. A quick way to get rid of something, by the way, is by using the minus sign on the vector and then the index. The minus tells R, hey, remove this index number. So if I wanted to remove the last one, which was we now have 6 in here, I can do that. So by putting the -6, and as you'll notice, R removes that. You can do this with other ones, like for example, I want to remove the first one, or I want to remove the second one, or I want to remove the first, second, and fourth one. Okay, so not only can you append vectors, but you can also remove them as well. So I'm just going to stick with illustrate that. But basically, we're going to take ages and put it back to what it was, which was removing the sixth element. By the way, an important function that we often use for vectors is the length function. The length will tell us how many elements are in there. Notice we didn't run this. So now if we look at the length of ages, you'll see that there's 5 elements in the vector there. One last important thing about vectors, we can have what are called named vectors, where we basically give names to the elements themselves. And the way we do this is just by putting the name and doing an equal sign for each input. So instead of thinking about, suppose I have a vector of different properties of one individual. So I'm not thinking about this column-wise in terms of data, but I'm thinking about this row-wise in terms of data. So suppose that I have information about some person named Bob. Their name may be Bob, okay? Their age may be 54. And their height may be, let's say, 5 meters. Okay, so one thing to note about vectors is that you can't mix types. I didn't mention the idea of type here in terms of vector. So you can have string vectors. Okay, you're not just limited to numbers. So you could say something like this is a string, and you'll have a vector of different strings. Right, something like that. Okay, so you can store strings of vectors. That becomes very useful in textual analytics. But here's the point: you can have named vectors, all right? And if you store this in a variable, you can then refer specifically to that piece of information by just giving it its name in parentheses. So if I want the age in that vector, it'll give me the age. If I want the name, give me the name. If I just simply want the name and age of that individual, it'll also give me that. Okay, so we can retrieve elements from named vectors not only by element number, because I can do the same thing I've done before with 1, 2, 3, etc. But I can also do this with the named vectors here. Named vectors are less common, but they do pop up from time to time. The next type of data structure we work with is the idea of a data frame. So if we think about a data set, a vector only represents a single row in a data set or a single column in a data set. But as is often the case of many data sets, we actually have tables of data where we have multiple individuals and multiple properties in the columns about those individuals. So we need a way to store the data in one format, and that format is what's called a data frame. So a lot of the times when you read data into R, as I'll show you how to do in a later video, R is going to read them in as a data frame. So you're going to need to know how to work with one. On the flip side, when you manipulate data, you also need to know how to create a data frame from vectors and other types of data structures. So we have two data structures here, two vectors specifically, age and income. I want to basically put them together into a table. And the way we can do that is by using the data.frame function and then just simply passing in the names of the variables, which are ages and incomes. So now if you take a peek into what's in my data, you'll see that it corresponds to each index in each vector. It basically just assigns it that row number. So if you had taken a look to see what's in ages and what's in incomes, you'll see basically by creating a data frame, it matched 30 with 55,000, 25 with 30,000, 41 with 65,000, and so on and so forth. So data frames can be created very easily if we first have started with vectors. There's other ways to create them, but I will leave that up to you to read in the book and in other sources. This is by far the most fundamental way that you can create a data frame. By the way, you can change the name of the columns by just using the same format we used before, where we have the name of the column, equal sign, and the vector. We did something similar with named vectors with values. We're basically doing the same thing with just the data frame. And as you can see, it named here the age and income. Data frames can also have row numbers. Okay, so suppose that I had the names of these individuals. And these names were, let's say, Bob, Sue, Kelly, Ahmed, and Shannon. Okay. There's two properties we often look at for data frames. The first is column names, which can very easily be found by using the names function. This is usually the first step we take when pulling in a data set from outside of R to take a look and see what names how are the columns named. This is also the same thing as using the command colnames. So if you run that command, you'll get the same exact thing. We also have the concept of row names, but as you can see here, they're just numbers. But basically, I want to reassign row names since I may happen to know those individuals' names. And one way of doing that is just by doing the same exact thing, but then just storing a vector of names, so long as the vector length is the same as the number of rows that are in your data frame. And if you check out what's in my data now, you'll see that it renamed the 1, 2, 3, 4, 5 to Bob, Sue, Kelly, Ahmed, Shannon. Okay, so as you can see, data frames are pretty flexible with respect to being able to change different properties of them. Important functions that we look at, the number of columns in the data frame, and the number of rows in the data frame. Length, I believe, does the same thing as the number of columns, but I could be wrong. It's just usually better to stick to n col and n row for more of an appropriate way of finding the number of rows and number of columns. We can also pull out elements from the data frame, and the way that this works is on a two-dimensional system. So we do it very similar to how we do a vector, but we have to provide two numbers, with some exceptions I'm about to mention, but two numbers. The first number is the row number, the second number is the column number. So if I say row number 2 and column number 1, it should return to me, let's see, row number 2, column number 1, it should return to me 25, which lo and behold, it does. If I wanted to pull out all of the columns for a given row, then what I can do is just simply give it a row, use a comma, and leave the column blank. Then what R will do is it will give me basically a named vector specifically for that individual. On the flip side, if I want to pull out all rows for a given column, I can do the same thing, but just leave the first entry blank and do the first one. So this will give me all the ages, for example. An alternative way of doing this is by the $ notation, where you ask it to give you a specific one. The alternative to this is also by just providing it the name. All of these do the same thing. Okay, so as you can see, very flexible. And by the way, you're not restricted to just pulling out one column or one row at a time. For example, suppose I only wanted the even columns. So 2, 4, 2 and 4, and I wanted all of the columns. Okay, so here, as you can see, I pulled Sue and Ahmed, who were 2nd and 4th in there. I can write conditions, which I'll get to at a later point in time, but we can also write conditional statements. So for example, suppose I wanted to pull only all of the data points such that the age is bigger than, let's say, 20 years old or 21 years old. And I want all columns for those. So let's take a peek at what this does. If we write this statement, okay, this is the trick to R as well as Python. Break each piece of this down. It looks complex, but it really isn't. Just break each piece down. This is the name of the data frame. The $ means I'm going to grab the ages. So if I take a look and see what that does, it's just giving me the ages. Now, when I put a greater than 21 here, let's see what that does. Notice that it's returning true, false values for each value. And what this is basically doing is just saying, is testing, is 30 bigger than 21? Yes, it is. Is 25 bigger than 21? Yes. Is 41 bigger than 21? Yes. Is 21 bigger than 21? No. Is 17 bigger than 21? No. So when you put in a vector of true false values into the rows with the same size vector as the number of rows, then R is just going to return those rows which are set equal to true. So if you happen to write any conditional statement, then you can basically refine the pieces of information that you're looking for by just writing those conditional statements. So I can design custom ones like my data, and I can do true, false, true, true, false, and give me all columns. And so what did it do? It gave me the 1st, 3rd, and 4th. And as you can see from the full data frame, 1st, 3rd, and 4th, Bob, Kelly, Ahmed, which is whom was returned. So as you can see, we can pull data from data frames in a lot of different ways. We can also provide it lists of names, so long as the names match the column names. Okay. And income. Right, so you can use those. So the way that we tend to work with the data frames is by working either on a number system, a logical system, or a naming system. You can do the same thing on the rows if the rows have row names on them. So for example, give me all information related to Kelly. because we have row names on here, R can very quickly pull those in. This will not work if we don't have row names, by the way. Okay, so those are the basics of data frames. The last is the notion of a list, and a list is an ability to store pretty much anything we want to store. Think of it as a dictionary where we give it a name and we want to store an object of some kind, anything. It can be a number, it can be a string literal, it can be a data frame, it can be a vector, it can be a different list, it can be anything you basically want it to be. Lists in R are the most flexible object that you can think of. So there's multiple ways to define lists. For example, I can define it, we define it using the list function, but I can define it explicitly by saying, let's say, the data is going to equal my data. The ages is going to equal the ages. And the incomes are going to equal the incomes. And why not? Let's throw one more. Let's do just an arbitrary one where we set it equal to the number 4. And if you take a peek and look what's in the list, you'll notice that this is what we call a named list, very similar to how we work with the data frame. But notice that it's storing all of my different pieces in here. Now, there's two ways to work with the list. I can work with them by numbers. Unlike vectors and data frames, lists work with 2 brackets, 1, 2, and then I can provide it a number. So you'll notice that in the first position, I stored my data frame. In the second position, I stored my vector, and in the fourth position, I stored a single number. Alternatively, I could have done this by name, and there's 2 ways to do it by name. The first is to use the same $ notation. The second is to use the bracket, double bracket notation, but to provide it with the exact name itself. Either way gives you the same thing. A lot of functions in R will return back a list to you in order for you to use. When that happens, you need to know how to work with the list. But it's not that complicated because, again, it comes down to either just working with the numbers or working with the names. If you're unsure, if a list has a name, because it doesn't always, you can just do my list and in the names function, and it will give you all the names. Last, you can define just define an empty list. Okay, by just using the list function with nothing in it, and then you can append things to it as you work. So I can say, all right, I've just worked on some results. I found the average age. I want to store this in my list. And more specifically, I want to store it under a variable name, under a name rather, that's called the average. Sorry, ages. Okay, likewise, suppose I have some more information, like I found the standard deviation of the ages, and I store it under another name that I give it, let's say the STD. And in a similar way, let's just say the range, right? So if we run those and you take a peek what's inside your list, you'll see that you are able to collect all of your results and store it in a very logical way. Now, theoretically, you can write all of these objects to your file system so that you can save it and work with it at a later point in time, because what you're working with right now is what's called in memory. It's not stored on your hard drive, it's stored on your RAM, but of course, when you go to turn your computer off, all of that's going to go away. So you may want to store information that you've just found or created. There's multiple ways to do this. They're storing it in an Excel format, in a CSV format. But if I have a more complicated object, like some of my lists here, the easiest way is to use what's called an RDS object, which is R's like binary format. And what you can do is say, save RDS. I want to save my list. And then you give it a file name, usually with the extension RDS. So you can say something like my results. RDS format is a very powerful format because it compresses things and minimizes the size, which is very useful. You may happen to notice here now I don't know where my workspace is, which is mildly problematic. I may have set it to Boston. Nope. So if you don't know where things are going or where things are being saved or where you should be putting files to eventually load, you can use the WD function. And R will tell you where in your computer it's pulling things from. Not WD, I'm sorry, get WD. So here it's saying it's stored in dynamic systems. So I have the folder dynamic systems, and there we go, there's everything. So as you can see, it's stored in RDS file. You can keep that on a disk somewhere, store that for long term. If you want to load that again, load that specific object, you can use the command read RDS and give it the name of the file, so long as that file is in the directory that getWD gave back to you. So you're gonna have to dig on your computer and kind of find that. I'm working on a Linux system, so that's why this looks like this. You will most likely be working on a Windows or a Mac system. Mac will look similar to this. Windows will be reversed, although R, I think, doesn't make a distinction with the slashes there. Anyway, you can read your work. You just make sure you store it in a variable. Okay, and basically what R is going to do is it's going to pull in that file. I misspelled my file name. It's going to basically pull in that file, and if you were to take a look to see what's in my work, you'll see it's the same list you had before, which you can then, pull different things out by giving it numbers or names, right? Give me the average of what happened here, and there you go. All right, so these are the three fundamental types of data structures in R: vectors, data frames, and lists. All three help us in our analysis of data, as well as doing other types of operations in our analysis. They aid in our ability to move large quantities of data around the system very easily. And they allow us to very quickly and easily save things in the long term, because sometimes a lot of people don't realize that data sets are pretty big. Their memory, what's called your RAM on your computer, may not be able to hold all of that information. So let's suppose that you only have 8 gigabytes of space of RAM on your computer, but you have, let's say, a 16 gigabyte data set. Your computer needs to physically move that data set from your hard drive to your RAM in order to actively work on that. You do have what's called swap memory, which the operating system itself does usually work pretty well with. But sometimes R will put restrictions in here to be able to work, to be able to, or will prevent you from being able to load such big pieces of data into R. We won't have a problem in this class because we're not going to be working with these humongous sets of data. But as you start to move to practice, you might find that you need to move to more cloud computing infrastructure, or tweak some things on your machine to be able to run the analysis on larger sets of data. Okay, so anyway, this is these are the three sets of data structures. We will be pretty much religiously working with these three types. You'll see me going back and forth in our coding throughout this semester, using these three types. But anyway, yep, those are our data structures. It takes some practice to get used to these. And you'll see me working with them, and that'll be a good enough of amount of practice for you to hopefully get the point.